Hello, today I'm going to talk about non-intrusive load monitoring, also known as NILM, and also known as energy disaggregation. So the agenda today is the following: what is ILM and what is NILM? Why NILM? The history. What does data look like? The ground truth, being manual or automatic setup, applying signatures, on-off, states continuous, the constraints, the algorithm, and finally the code. So what is ILM and NILM? ILM stands for Intrusive Load Monitoring. And what happens here is that each appliance has a smart plug that records the power and energy consumption for each appliance. Now with NILM, which stands for Non-Intrusive Load Monitoring, each appliance does not have a plug. Instead, at a central location, there will be a smart meter that collects all the energy information from the devices without each one being monitored. So why NILM? According to several studies, it has been shown that with real-time feedback, consumers can save up to 12% of annual electricity. And in fact, if you look here at this chart in Canada, we see that residential energy consumption is 13%, which is quite significant. If you can reduce that by 12%, that would be a great contribution. As well, if you were to have smart plugs at each appliance, they cost around $50 each, and in a home you may have about 10 or more, meaning you can have up to $1,000 or even more. Plus, you have to monitor the smart plugs. If you have new appliances, you have to buy new smart plugs. If they fail, you have to replace them. So by using NILM, we help reduce electricity consumption and also help with monitoring without spending money with monitoring. So a bit of history. NILM was invented by George Hart, Ed Kern, and Fred Schrepp of MIT in the early 1980s and was research funded by the Electric Power Research Institute. It is known as the Hart paper. And since that time, 1984, it has been an active area of research. And today it has gained lots of traction because of machine learning and deep learning methodologies. So what does the data look like? Here we see a picture of energy consumption, so the power across time. And we can see here that when there's an event that goes up, meaning that the power is turned on, we can see that, for example, a refrigerator is turned on and then turned off. Then an oven is turned on and then the oven is turned off. Also, an oven and a refrigerator can be turned on at the same time. Same with the stove burner. So it can be quite complicated, and we will find ways to break this down. So generally, there's two approaches with NILM to find the ground truth. One of them is manual, and another one's automatic. So with manual, what happens is that for about a month or so, you monitor each appliance, and you record when it is turned on and when it is turned off. And this can be done with temporary smart plugs. So that's the manual setup. The automatic setup, on the other hand, for 1 month, the data is analyzed. Instead of there being each appliance, we take the full energy consumption and derive from it what appliances there are. So here in the picture on the right, we can see that with regards to reactive power and real power, the refrigerator is on with positive real power, positive reactive power, and turned off by the same amount with a negative reactive power and the negative real power. So that's a way that we can determine what appliances there are. This is also called clustering too. So overall, there's 3 types of appliances. We have ones that are on and off. So this is called the type 1. An example would be a light. You turn the light, it stays on throughout the whole time until you turn it off. Next, we have a type 2, which is multi-state. What that means is that you can turn it on, but it can have several states inside before it's actually turned off. So for example, washing machine, right? You turn on the washing machine. It can spin, it can dry, it can rinse. And each one of these steps requires a different consumption of power. Finally, we have continuous. And with continuous, it's not a stepladder thing, it's a continuous thing. So for example, power drills, they consume continuous energy. Generally, type 1 is the easiest to analyze. Type 2 is second. And in fact, sometimes type 2 can be analyzed as if it was several type 1s at the same time. And continuous, actually, this is not done a lot in residential properties. Instead, it is done mostly in industrial properties whereby they have industrial tools. So there are some constraints or assumptions that we do in order to make NILM to work. The first one is called the switch continuity principle. So basically, in a small time interval, we expect a small number of appliances to change state. We have the zero loop sum constraint, which means that power is turned on or turned off. There is no leftover. It is the sum is zero. And finally, we have the uniqueness constraint, which states that the appliance has distinct operating power levels. The general algorithm is the following. We collect data. We process the data by removing noise, for example, or normalizing the data. Then we do what's called edge detection. So we figure out what the on states and off states are. Okay, and from this, we can extract the features and determine what types of appliances are turned on. Okay, then we do appliance classification to figure out which appliances turn on, and then we can disaggregate to figure out which appliances turned on. Now, when you train the model and you try to figure out the appliances, you cluster or do something similarly, but you're not able to determine which cluster belongs to which appliance. Okay, so what happens is that there is no, unless you know the appliances directly, you cannot know for sure which appliance it is. But you can do a match with known appliances. So for example, if I know that on average a refrigerator has this certain profile, and what I find in my data matches similarly, then I can say that this signature does belong to a refrigerator. So at first we train, and then once we have the training, the signatures, this is used in the classification to determine at what time sequence what appliance it is. Okay, now we go to the code. Here I use the AMPDS2, which is the Almanac of Minutely Power Data Set. It is from British Columbia. There are over 1 million readings for 2 years of monitoring from April 2012 to March 2014, and this is per meter. There are a total of 21 power meters, 2 water meters, and 2 natural gas meters. And the consumption was at, the report was at a 1 minute frequency. And what happens is that in the application that I'm using, this data set is actually changed to the H5 format. And this format captures everything that is taken from the data, but just changes it into a format that's much easier to use with the NILM TK library. So first what happens is we have to get the libraries for the application. And here we have the classic mathematics libraries, pandas for data analysis, NumPy for algorithms. And we also have NILM TK, which stands for NILM Toolkit. NILM Toolkit is an open source initiative that was created by enthusiasts in the field of NILM. So their attempt was to make to consolidate all the research into this tool. So at first we initialize the data. Okay, we get the data set. We split it 80% train and 20% test. Okay, and we can take, this is the plot of the train. Okay, at the bottom you see the energy profiles for each appliance. Okay, for example, heat pump, light sockets, television, electric oven, and much more that were not specifically labeled. And the blue chart at the top, that is the overall consumption pattern, consumption based on the addition of all of these appliances. And this chart is for the test data. So this is the aggregate power sample from all the appliances together. Okay, next what we do is that we figure the top 5 appliances. Okay, now what happens here is that we do have a loop, and in this case we test out 2 classifiers, one called combinatorial optimization, another one called factorial HMM, hidden Markov model. These 2 were, you could say, the original algorithms done, and since that time many other algorithms have been developed, and now most recently there have been deep learning algorithms. So what happens here is that we train first. We determine the signatures of the top 5 appliances within the training period, which was 80%. And we also run a prediction which with the test data to see if appliances are correctly predicted. So this is the script, and basically what happens is this. First of all, we disaggregate the prediction. So we separate into chunks, and each chunk we evaluate the power consumption. Okay. Then what we do is we do the prediction and ground truth. So for each chunk, we do a prediction, and we also figure out the ground truth. Ground truth being what appliance actually did it, and the prediction being what we think based on our training the appliance is. Okay. Number 3, we combine the results. Number 4, we match the data and the time zones. So for example, we have data for the predicted and the ground truth. So we want to match them up so that they occur at the same time. And the output is that we return the ground truth and predicted data back to the application. Okay, so combinatorial optimization is a NILM algorithm. And what happens is that you try to search for the optimal combination of appliances with the total power closest to the aggregate. And this is usually done with the genetic algorithm. So what happens is that we're trying to find the best from the many. It deals with problems where there are a large number of possible solutions, and the goal is to identify the optimal one. And we're also optimizing the goal. This optimal solution minimizes or maximizing a specific objective function, such as minimizing travel time or maximizing profit. So that's combinatorial optimization. Next, we have factorial hidden Markov model. So basically what happens is that when you're given a time states, FHMM predicts the combination of active appliances energy usage that contributes to the aggregated energy. So what happens is that it tackles multiple time series and can analyze several time series happening simultaneously. The hidden states capture interactions. And finally, we get the results. So what we do here is called RMSE. Okay, and RMSE measures the average difference between the predicted and actual result. It penalizes large errors, and the goal is to be as low as possible. So here in this chart we have here for combinatorial optimization and FHMM, we see the different root mean square error results. Okay, we did it for the top 5 appliances. 3 of the appliances we don't know exactly, they don't have a label, but 2 of them, one was heat pump and one was fridge. That concludes the NILM presentation. I hope you enjoyed, and I hope that you will have a good time in this really exciting field. Thank you very much.